Array antennas, linear arrays, series on antennas and wave propagation, lecture number 3.12. Linear array refers to a group of antennas arranged over a straight line and operated as a single unit. Different modes of operation are possible with the linear arrays. Broadside mode and fire mode are most important modes. Linear arrays may also be associated with grating lobes, which represent power wastage. Linear arrays may also be fed with non-uniform currents, like in binomial arrays and Dolf-Chebyshev arrays. All these aspects pertaining to linear arrays and also some more interesting aspects like principle of pattern multiplication are discussed, described and explained in the present session. We begin the session by considering different modes of operation possible for linear arrays. Important modes are broadside mode, end fire mode, backfire mode, end fire mode with ID, backfire mode with ID. ID stands for increased directivity. In case of broadside mode of operation, direction of maximum radiation is normal to length of the array. Mathematically, that direction can be described as phi equal to 90 degrees. Normal to length of the array implies it may be upwards like this, it may be downwards like this, it may be out of the screen or it may be into the screen. All these directions are normal to length of the array. In fact, any direction that falls over a plane which is normal to length of the array is direction normal to the array. End fire mode. In this mode, when the array is functioning in this mode, direction of maximum radiation, it exists along the length of the array. This is the direction along the length of the array because the array starts here at the other end, 0th element, element 1, element 2, element 3, element 4. This is last element, n minus 1th element, or first element, second element, third element, fourth element, nth element. This direction is mathematically described by phi equal to 0 degrees. Then backfire mode. Array is said to be working in a backfire mode when it radiates maximum in the direction opposite to length of the array. This is length of the array direction. Opposite to length of the array means this is the direction. This direction can be described by phi equal to 180 degrees. Notice this is phi. This angle is phi. Its range is 0 to pi or 0 to 180 degrees. End fire mode with ID. This is another mode, important mode. The speciality of this mode is it gives more directivity than given by ordinary end fire mode. In this case also, end fire mode with ID also, direction of maximum radiation is along the length of the array. Another mode is also there, backfire mode with ID. In this case, direction of maximum radiation is opposite to length of the array, means leftwards, like in case of backfire mode. When it comes to direction of maximum radiation, end fire mode with ID, both have same direction of maximum radiation. Backfire mode and backfire mode with ID, they both have same direction of maximum radiation. Also, end fire mode and backfire mode, Their performance is almost same except for the difference in directions of maximum radiation. Similarly, performance of end fire mode with ID is almost same as performance of backfire mode with ID operation except for the difference in directions of maximum radiation. Of course, phase progression alpha takes same value but opposite polarity in case of end fire mode and backfire mode. In the same way, value of alpha phase progression is the same in end fire mode with ID and backfire mode with ID. Same value but opposite sign, opposite polarity. Now we discuss about these modes a little bit more elaborately. First we consider broadside mode. In this case, direction of maximum radiation is in a plane normal to the length of the array, that is phi equal to 90 degrees. Notice in broadside mode of operation, direction of maximum radiation is not 1. In reality, it is infinity. Direction can be any one, but it requires to be in a plane normal to length of the array. Phase function in general, it is beta d cos phi plus alpha, and it has to be 0 in the direction of maximum radiation. This is general point conclusion we have arrived in the discussion in a previous session. So along the direction of maximum radiation, phase function psi has to be 0. General expression for psi is beta d cos phi plus alpha, but it is 0 along direction of maximum radiation. Direction of maximum radiation is along phi equal to 90 degrees. Therefore, beta d cos 90 degrees plus alpha has to be 0, giving alpha equal to 0, and hence to operate in this mode, excitation currents of the array must be in phase. Alpha has to be 0 to operate a linear array in broadside mode. Alpha is phase progression. In this mode, the phase function becomes psi equal to beta d cos phi because alpha is 0, and psi changes from beta d to minus beta d through 0 as phi is varied from 0 to pi through 90 degrees. This is array, this is phi. Phi varies from 0 to pi. This is the range. 0 to pi is the range of phi. As phi is varied from 0 to pi through 90, naturally psi varies from beta d to minus beta d. For a uniform broadside array, the product of directivity and 3D beam width in degrees is this product with some analysis. It can be found equal to 101.5. These are some important points regarding broadside mode operation of linear array. Here is shown patterns of broadside arrays. So here is array along z-axis. Notice radiation is maximum in the plane normal to the array like this. This is the plane normal to array. So here it is maximum. In B is shown an array. Here also it is along z direction. This array is radiating in broadside mode like this here. Not only that, it is also radiating in end fire as well as backfire 2 or backside 2. We discuss about arrays radiating both in end fire and broadside together simultaneously later in the session. Now end fire mode. Direction of maximum radiation is along the length of the array, phi equal to 0. Then the array is said to be working in end fire mode. This is length of the array. First element, nth element. This is phi. This is phi. Phi is 0 is the direction of maximum radiation. In case of end fire mode, it means it is like this. Maximum radiation is along the length of the array. Phase function is to be 0 in the direction of maximum radiation, that is psi is equal to beta d cos 0 degrees plus alpha is 0, giving alpha equal to minus beta d. Hence, to operate in this mode, the excitation currents must be fed with a progressive phase shift alpha equal to minus beta d. If we want the array to work in end fire mode, we have to ensure that phase progression of the excitation currents must be conforming to this relation alpha equal to minus beta d. Notice beta is 2 pi by lambda, phase shift constant. Lambda is wavelength corresponding to operating frequency of the array. D is spacing, element spacing. In this mode, phase function psi is equal to beta d cos phi minus 1. How this thing has come? General expression is beta d cos phi plus alpha, but alpha is minus beta d in case of end fire operation. Therefore, psi becomes equal to beta d cos phi minus 1. And it changes from 0 to minus 2 beta d through minus beta d as phi is varied from 0 to pi through 90 degrees. When the spacing d equal to lambda by 2 for this particular spacing, there exists two identical end fire lobes, one along phi equal to 0 degrees and other along phi equal to 180 degrees. However, one of them can be eliminated by reducing the spacing to less than lambda by 2 multiplied by 1 minus 2n. n is number of elements. Lambda is, as already mentioned, wavelength corresponding to the operating frequency of the array. D is spacing, of course. What he says is when D is lambda by 2, then array starts radiating not only along the length of the array maximum, but also maximum opposite to along the length of the array, that is in this direction. And radiation in the opposite direction, it may be unwanted. We want radiation maximum only in one direction most of the times. So the second direction radiation, it has to be eliminated, and it can be eliminated by arranging the inter-element spacing satisfying the relation given here. End fire with ID. This mode comes into being when excitation currents have a progressive phase shifts of minus beta d plus pi by n or beta d plus pi by n. One or 2 points before going further. What is the difference between end fire and end fire with ID? End fire with ID gives more directivity than ordinary end fire. This is one aspect we have to keep in mind. Second aspect, when it comes to direction of maximum radiation, it is the same in end fire and end fire with ID. Second point. Now third point, when it comes to phase progression in excitation currents, it is minus beta d in ordinary end fire. It is minus beta d plus pi by n in case of end fire with ID. Now, when we set alpha equal to beta d plus pi by n, then maximum radiation is opposite to the direction of maximum radiation when alpha is minus beta d plus pi by n. It implies in this direction. In the first case, maximum radiation is like this. Along the length of the array, phi equal to 0. This is the situation. When alpha is set to beta d plus 1, direction of maximum radiation is along phi equal to 180 degrees. It gives same increased directivity as given by end fire with ID, radiating maximum along phi equal to 0. Now, let us move further. The corresponding array phase functions are psi equal to beta d cos phi minus 1 minus pi by n. It can be expressed as 2 pi d lambda cos phi minus 1 minus 1 by 2n. This is the situation when direction of maximum radiation is along phi equal to 0. When direction of maximum radiation is along phi equal to 180, then psi is beta d cos phi plus 1 plus pi by n equal to 2 pi d lambda cos phi plus 1 plus 1 by 2n. How this expression has come into being? General expression for psi array phase function is beta d cos phi plus alpha. If we substitute expression for alpha minus beta d plus pi by n, we get psi here like this. Or if you use alpha expression as beta d plus cos pi by n in the general expression for psi, we get this expression. It's not a big thing. So these are phase functions with maximum radiation along or opposite to length of the array. Psi equal to 0, 180 degrees direction. In either case, element spacing must be 1/4 wavelength. This is the condition. If we want increased directivity from the array, we have to ensure that it must be even less than 1/4 wavelength. The phase function psi changes from minus pi by n to minus 2 pi plus pi by n, as phi is varied from 0 to pi when maximum radiation is along phi equal to 0. When radiation maximum is along phi equal to 180 degrees, psi changes from pi by n to 2 pi plus pi by n, as phi is varied from 0 to pi. So here is shown end fire, backfire arrays. This is the length of the array. Here this is element 1 or 0th element. This is last element or n minus 1th element, or this can be considered as first element, this can be considered as nth element. In A, notice direction of maximum radiation is along the length of the array. Here it is opposite to length of the array. Phi is direction of maximum radiation is 180 degrees. Of course, when array is over z-axis, phi becomes equal to theta. It is theta. Here is shown properties of uniform linear arrays at one place so that one can understand them easily. Uniform linear array. Array means group of antennas being operated as a single unit. Linear, when they are placed over a line, then array becomes linear array. Uniform means the individual elements of the array is placed over a straight line and fed with currents of same amplitude. Phases of the currents may change. So end fire with ID mode is there, broadside mode is there, end fire mode is there. Broadside mode. Directivity can be found nearly equal to 2 times L by lambda. L is length of the array. In case of end fire mode, directivity is 4 times L by lambda. Notice end fire mode gives you more directivity than broadside array. In case of end fire with ID array, directivity is 1.789 times 4L by lambda, which is 4L by lambda is directivity given by end fire, ordinary end fire array. So end fire mode gives more directivity than broadside. End fire with ID gives much more directivity than broadside and more directivity than ordinary end fire. When it comes to beam width, first null beam width of broadside array is 2 times lambda by nd. In case of end fire, it is twice square root of 2 lambda by nd. In case of end fire with ID, it is 2 times square root of lambda by nd. When it comes to field pattern or array factor, for broadside mode, E is 1 by n sin n psi by 2 by sin psi by 2 within mod. In case of end fire mode, E is 1 by n mod sin n psi by 2 by sin psi by 2. In case of end fire with ID, E is sin pi over 2n sin n psi by 2 by sin psi by 2. So these are important aspects pertaining to uniform linear arrays when they are working in different modes. Before going further, directivity, first null beam width and array factor of backfire mode or backside mode, they are same as end fire mode. Similarly, directivity, beam width and array factor of backside or backfire with ID mode, they are same as end fire mode with ID. For this reason, they are not shown separately here. Now grating lobes. what are grating lobes? Consider end-fire array. This array radiates maximum along phi equal to 0 direction. Sometimes it happens when certain conditions are met, this array starts radiating maximum in the opposite direction too. In this direction also, it starts radiating maximum. It may even start radiating in broadside mode also. What we want is maximum radiation only in one direction, but here it starts radiating maximum in other directions also. The radiation in any direction other than wanted direction is a wastage. Grating lobes indicate a radiation in unwanted directions. Now let us move to understand the grating lobes in a more detailed manner. The lobes containing maximum other than main maximum, for them psi by 2 is equal to plus or minus m pi, where m equal to 1, 2, 3 in the pattern of an array antenna. These are called grating lobes. They come into being when the inter-element spacing is sufficiently large to permit the in-phase addition of radiated fields in more than one direction. Grating lobes are absent in the pattern of a broadside array unless the inter-element spacing is more than or equal to one wavelength. So here is a point. Grating lobes are always unwanted and they can be made absent by selecting element spacing less than lambda in case of broadside operation. Grating lobes can occur only when spacing of elements is more than or equal to 1/2 wavelength in case of end fire. Here end fire should be there, so we added. So in case of end fire mode of operation, grating lobes can be avoided by seeing that element spacing is less than lambda by 2. In case of broadside, it is less than lambda. In case of end fire, it is less than lambda by 2. After having some understanding regarding array modes and grating lobes, now we move to array features. As already mentioned, arrays are group of antennas operated as a single unit. So array is an antenna. It works as a single individual antenna. Inside there may be several antennas, but it can be looked upon as a single antenna. Hence it is associated with directivity, it is associated with beam area, it is associated with total radiated power, it is associated with radiation intensity, it is associated with the field intensity. All the parameters, all the quantities with which a single ordinary antenna is associated with, all those things they also appear, they also get associated with arrays. Radiation intensity of an array, it can be found from the sequence that is shown here. First, we have to find out power density. S stands for power density. Power crossing unit cross-sectional area. It is equal to Et square by 2 eta. Et is radiation field intensity at a field point P. An expression for Et has been given in a previous session. So it is available. From Et, S can be computed. From S, one can get radiation intensity U by multiplying it with the radial distance of the field point. Similarly, total radiated power can be computed from S by integrating S over a spherical surface. Total radiated power can be obtained. Directivity of the array can also be determined. How? D is 4 pi U max, maximum radiation intensity by total radiated power. This is total radiated power. U is available from this maximum value. U max can be obtained. Substituting those two quantities in the expression D, one can get directivity. Beam area. This is the expression for beam area. Of course, another expression is one can use this expression also, 4 pi by d. This way also one can get omega A. So point is, before going further, all quantities of interest pertaining to arrays, they can be obtained by following the procedures that we followed in case of single individual antennas like dipoles, monopoles. Here is given properties of different modes of linear arrays: broadside array, end fire array, end fire with increased ID, directivity, directions of maxima, directions of nulls, directions of nulls for large arrays, first null beamwidth for large arrays. So all these quantities for broadside array, end fire with ID, increased directivity, for all these modes, they are listed here. Finding them is not that much difficulty. Some properties are listed in the previous slide, some more are listed here. Directions of half power points, half power beamwidth for large arrays, directions of minor lobe maxima, first side lobe beamwidth, these are all listed here. For broadside array, end fire array with increased directivity. These two slides give complete total information pertaining to three modes of operations of linear arrays. Now we move to binomial arrays. What is binomial array? Before going to that, we have to consider a uniform linear array. What is uniform array? Uniform array means the excitation currents to the array, if they are same, if they are uniform, then it is uniform linear array. If here current is 1 ampere, let us say here also 1 ampere, here also 1 ampere, here also 1 ampere, here also 1 ampere, current to each and every element must be same 1 ampere. This is the property of uniform linear array. Then what is binomial array? The currents into elements of the array are proportional to binomial quotients. Then that array is called binomial array. People go for binomial arrays to eliminate side lobes. The advantage of binomial array is side lobes, they are absent. With this information, let us move further to understand binomial arrays a little more deeply. Binomial arrays are linear arrays operated always in broadside mode. So binomial arrays are linear arrays. Their operation is broadside, that is alpha equal to 0. The principal feature of their pattern is very low side lobe level. In fact, no side lobes exist for half wavelength spacing when d is less than or equal to lambda by 2 in its pattern, and hence no nulls other than the two surrounding the main beam are present. So it's a matter of side lobe level, low side lobe level or zero side lobe level in case of binomial arrays. The ratio of excitation currents into various elements, that ratio is like this. It is given here in the form of Pascal triangle: 1, 5, 10, 10, 5, 1. If it is, let us say, 6 element array, consider 6 element array. If the current into the first element is 1 ampere, second element it must be 5, third element it must be 10, fourth element 10 amperes, fifth element 5 amperes, sixth element, last element 1 ampere. These are all binomial quotients. Radiation pattern of binomial array, it is given here. When the number of elements is even, array factor even. If the number is 2m, then array factor is sigma 1 to m an cos 2n minus 1 pi d over lambda cos theta. In case of odd number of elements is equal to 2m plus 1, odd. Array factor is sigma 1 to m plus 1 an cos 2n minus 1 pi d by lambda cos theta. Beam width of this array for a spacing of half wavelength, and in case of isotropic element array, half power beam width is given by 1.06 over square root of n minus 1 equal to 1.06 over square root of 2l lambda. L lambda means length in terms of wavelength. This half power beamwidth is in radians. Array directivity can be found equal to 1.77 square root of n. It can be shown equal to 1.77 square root of 1 plus 2 L lambda. These are properties of binomial array. These quantities are obtained after doing analysis, rigorous analysis. Certain disadvantages are there associated with binomial arrays. They are described here. Major disadvantages are larger beamwidths and lower directivity. Notice, binomial arrays can give us no side lobes or lower side lobes. But beamwidths associated with binomial arrays is large. Directivity is also large. These two are drawbacks, main drawbacks. Both are caused by inefficient use of available length, since the excitation amplitudes are made proportional to binomial quotients, and hence elements near the ends of the array are weakly excited. Small contribution to the total field from the elements near the ends of the array is equivalent to a reduction in the effective length of the array, resulting in a decreased directivity and larger beamwidth. What he is telling is, this is array. Notice at the end elements, the excitation currents into these elements is small when compared to currents into the elements that are in the middle. It implies inefficient use of the end parts of length of the array. Naturally, it leads to decrease in effective length of the array, decreased directivity and a larger beamwidth. Another disadvantage is in difficulty to maintain wide variation between the amplitudes of the currents into various elements, leading to very low efficiency. Another drawback. We have seen in the first element, if the current is 1 ampere, next element it is 5 amperes. Large variation. 1 ampere, 5 ampere, then it may be 10 ampere, something like that. Roughly I am telling you. Maintaining large variation, it is difficult and it leads to a very inefficient system. A comparison is given between broadside and fire with ID and binomial with D equal to lambda by 2. Directivity, half power beamwidth, normalized array factor. These are all given, shown in this slide here for all the 4 arrays. Notice these 3 are uniform linear arrays, whereas last one is non-uniform but symmetric linear array. Now we consider a beautiful principle, quite useful in determining the pattern of arrays. Principle of pattern multiplication. It is highly useful. This principle is highly useful in finding the radiation patterns of arrays with non-isotropic but similar elements. It is applicable to arrays of any length provided the sources are similar and of a finite size. Also, it is equally applicable to both space patterns and plane patterns. What is principle of pattern multiplication? Here is a uniform, let us say, uniform linear array, and elements of this array are isotropic, and it is giving a pattern. Let us denote that pattern by ET. This is with isotropic elements. Isotropic. Now we have an array. This array consists of several elements and they are identical. And let us also suppose that they are directional. They are not isotropic. Elements are identical but not isotropic. We want, let us suppose, we want its radiation pattern ET. According to principle of pattern multiplication, ET of array with non-isotropic elements is equal to product of pattern of the array with isotropic elements, this one. Let us call it ETI. ETI with unit pattern. Unit pattern means radiation pattern of the any one element in the practical array. Directional pattern of the elements in the array. Usually it is denoted by E0. Product of these two gives us radiation pattern of the practical. Now, a statement is given here. Let us go through it. The total field amplitude pattern of an array of non-isotropic but similar sources is product of individual source pattern. It is called unit pattern, and pattern of an array of isotropic point sources, each located at the phase center of the individual source and having same relative excitation amplitudes and phases as the non-isotropic point sources. Mathematically, E is f of theta phi multiplied by f of theta phi, where small f is unit pattern, capital F is group pattern or array factor or field pattern of isotropic array. This principle is quite useful in computing patterns of arrays consisting of directional elements. Here is shown arrays: uniform array, Dolf-Chebyshev array, another Dolf-Chebyshev array. Here is shown binomial array, side lobe level, side lobe level, side lobe level, side lobe level. Side lobe levels of these 4 types of arrays are considered. Similarly, beam width, they are also considered. Gains are also given. Notice in case of uniform array, excitations are same. In Dolf-Chebyshev, excitations are varying, increasing and decreasing. In the third one also increasing, decreasing, but this increase and decrease is not same as in the second one. Binomial, this increase or decrease is also not same as in the previous 2 cases. Also notice here excitations are symmetrical in second array, third array and fourth array too. Symmetrical about the center of the array. Non-uniform but symmetrical. With this we come to an end of the session. In this session, linear arrays are introduced, different modes of operation, grating lobes, different features are all given, described and explained. Binomial arrays are also introduced along with their merits, demerits, in addition to principle of pattern multiplication. Hope this session is useful to you. We meet again in another session with a new topic soon.